All right. Okay.
Okay.
And over to you. Thank you.
Yeah, sure. Welcome everyone to our sessions in image segmentation. So we have 3 speakers in this session, presenting their work in various topics in image segmentation. Our first speaker is Bing Kong from Korea Medical. Okay, cool. So yes, Korea will present their works on ultrasonography, uterus and fetal segmentation with constrained spatial temporal FCN. Now I will hand it over to Bing. Thanks.
Hello, everyone can hear me, right?
Yes, we can.
Oh, great. Yeah, so, I'm Bing Kong, and nice to meet everyone, and thanks for attending the meeting. And yeah, so I will present today. So, just a brief introduction for this paper. So, this is about the automatic segmentation of uterus and fetus as from 3D fetus fetal ultrasound images. So basically, there are 3 major challenges regarding this problem. So as you can imagine that this is a really small data set, right? So I think this is this problem is kind of really usual regarding our medical image segmentation problems, right? So for our data set, it's kind of like just have 40 or 50 images in total. So as you can imagine that right now we usually use 3D convolutional neural networks to do the segmentation, right? So with a large 3D convolutional neural network, it's really easy to overfit the small neighbor data set, right? So the second challenge is that sometimes the 3D images is anisotropic, right? So which means that the spacing between the voxels are different from different directions, right? And the third challenge is that without as you can see in this figure, so the subfigure B is the segmentation result obtained from the 3D convolutional neural networks, right? So the fetus leaks into the other areas, right? Because it doesn't consider the spatial correlations, right? So if we just use 3D convolutional neural networks, it's impossible to incorporate this kind of spatial correlations between the objects, right? So then it comes to our framework for the joint segmentation of uterus and the fetus for the segmentation. So it consists of 2 components. So this is the framework. So for the first part, we use 2D convolutional neural networks, right? So why we just use 2D neural networks? Because as I mentioned, that 3D convolutional neural networks is really prone to overfitting problems, right? So with just this small data set, we would like to reduce the number of parameters, right? And so after we use this kind of 2D neural networks to extract the object specific features from the image, we use bidirectional convolutional or LSTM to consider the interdependencies between the different slices. And finally, we use two decoders. So the first decoder is used to predict the filters, and the other one is used to predict the outliers. So basically, that's the framework. So yeah, and finally, so this is our the third contribution. So as you can imagine that if we just use a typical neural network to do the segmentation, it's impossible to consider the the spatial coordinations between these two objects, right? So we introduced a novel north to consider these coordinations. So so basically, it's kind of like a similar to the dice north, right? But so this is the equations. The denominator is the intersection between the filters segmentation and the outliers prediction, and the denominator, the following part is the prediction of the filters, right? So as you can imagine that if the filters is not fully contained within the outliers, the loss will be larger than 0, right? So otherwise, if it's fully contained within the outliers, the loss will become 0, right? So the larger, I mean, so if a major part of the filters is outside of the outliers, the loss will be really huge, right? And so as I mentioned, that the data set is really small, so the total number of data set is just 45, right? So it's impossible for us to get more data sets because it's really expensive. And this data set is captured from 20 patients. And the ages of the patients ranges from 11 to 17 weeks. And we randomly split the data set. So in the patient level, so we use the 70 patients for training and 3 patients for the evaluation. And for the pre-processing, we manually copied the outliers regions from the water volumes, and then further resampled the images into 224 by 224 in the XY dimension, and for the z-axis, the images remain the same. And we compared with our method with three state-of-the-art method so the first one is 3D neural net, and the second one is 3D attention neural net. Yeah, so it's and we also compared our method without the introduced noise. So as you can see, generally our method is outperforms other method, and with our novel noise, our method further boosted the performance. And so this is the quantitative results. So this is the input, right? And the second column is the ground truth, and the third column is the result obtained by the 3D unit. And as you can see, this one, the result is not satisfactory, right? So there is the Utter's prediction leaks into the outside of the factors, right? And using the novel noise, our prediction is fully contained within the ultras. Yeah, so this is the further results. And yeah, so for the summary, so the first one is that we divide the problem into into easy to solve sub problems, right? So instead of solving, we noticed that we can first use the 2D convolution neural networks to extract the object related features, right? And then we can use the two-directional LSTM to consider the interdependencies between the features, right? So this is our first. This is the first observation, and the second observation is that we can use prior knowledge in noise, right? So we can use this kind of we can incorporate this kind of spatial constraint into the segmentation noise. So by combining these two methods, our method can outperforms the baseline. Yeah. So I think that's it for my method, for my talk. Yeah. So I think I still have 3 minutes. So any questions?
Interesting talk. Are there any questions from the audience? I saw there's questions from the chat. Let me read the question. So why did you rescale all images into 224 by 224? Will this cause any image quality loss? And also, have you done the same pre-processing for all compare methods?
Oh yeah. So yeah, so let me see. Yeah, this is a really good question. Yeah, thank you so much. Yeah, so for the first question, why do you rescale all the images, right? Yeah, so for our data set, so the image sizes are kind of different. So you have 512 by 512, right? And some of them are different sizes. So we have to normalize them to into the same sizes in the XY dimensions, right? And for the Z dimensions, it doesn't matter because we use LS team, right? So, but in the XY dimension, we have to resize it into the same sizes. Otherwise, we cannot feed them into the 2D convolutional neural networks, right? Yeah. So as I mentioned, that is we just the biggest size is 512 by 512. So the image quantity loss is not a big deal, right? And for the final question, yeah. So yeah, we use the same pre-processing for all the comparator methods. Yeah.
Okay. Thank you, Bing, for the question.
Yeah. Thank you.
One question.
Yeah, please. Please, we have time for
One of your pre-processing steps was delineating the uterus manually. So what is the impact of that? If you don't delineate the uterus manually, which was the critical part comparing your visual results with the other ones, what will be your result?
Just to clarify, you mentioned that why do I manually crop these regions, right?
Yes. So one of your pre-processing steps you mentioned that was a manual delineation.
Yeah. Yes. So that's a really good question. Yeah. So as this project is done a long time ago, yeah. So as I can remember that, for the fetus and the uterus region is kind of a small region of the image, right? So it's really hard for the and the data set is really small, so we have so it's really hard to train a satisfactory neural network to do the segmentation. So that's why we use we have to manually focus the uterus regions. Yeah.
Okay. Thank you. I guess we should move on to the next speakers now, and let's thank the speaker Bing again for the nice talk.
Yeah, thank you so much. Yeah.
So our second speaker is another Rajput from the University of Warwick. So yes. Okay. Yes, please. So Roger is from the University of Warwick, and he will present the works on a normal frameworks for coarse-grained semantic segmentations of host-like images. And now I look forward to your talk, Roger.
Good morning, everyone. Thank you for the introduction. My name is Saad, and sorry. No. There we go. All right, sorry for that. So my name is Saad Bashi, and I will be presenting our work in collaboration with Mohammad Shaban, Arif Puram, Shani Raza, and Nasir Rajput. The title of our work is a novel framework for coarse-grained semantic segmentation for whole-slide images. The outline of my talk is that I will introduce about the problem and its solution, the data set we used, the proposed method, and the experiment results we did, and finally the conclusion. So basically, we use semantic segmentation to extract regions from a whole slide image that can be tissues, different tissue sections, tumors, stroma, or nuclei, glands, all those for different kind of downstream analysis that can consist of statistical structure or spatial relations we explore from our WSIs. For semantic segmentation, we have different approaches. One of the approach is using pixel-wise segmentation algorithms, where we use DeepLab, UNet, and other networks. And we have pixel-wise ground truth, which is very fine-grained. And it's very expensive because we need experts. And normally it takes around 4 to 5 hours to annotate WSI exhaustively. Especially in nuclei, it can go beyond that because we have to mark nuclei boundaries very precisely. It is very computationally expensive in getting ground truth and training. So the other option is, which is cheaper, is patch-based segmentation. We have a simple patch of size, and we have a simple one label, either it's tumor or stroma or anything. It can be any label. It's not very accurate because we lose some kind of context. So if we increase the context, we can lose the speed. So there's a trade-off between context versus accuracy. So considering the cons of both, we proposed a coarse segmentation. It is computationally fast, and we'll see later on. It requires coarse annotations. It doesn't require fine-grained annotations, and it's applicable where we do not need exact, accurate estimation of the underlying subject. For example, nuclei, we can't do that. But for glands, layers, other sections, tissue areas, we can do that. As you can see on the image on the right side on top, if we just do the coarse segmentation, we'll get a smaller mask. It's been rescaled for design purposes. And you can see the pixelated area as well is because of its coarse. And on the bottom, you will see the pixel-wise perfect annotation, which is expensive though. So the dataset we used was oral epithelial dysplasia and head and neck squamous cell carcinoma. Both datasets were annotated by our pathologist, Arif Puram from Sheffield. So he annotated one dataset for pixel-wise annotations, like properly, which takes time. And the other one, he did the coarse annotation. So we didn't have pixel-wise annotations for that dataset. It's large as well. So first, we from pixel-wise segmentations to prove that it works comparable to our coarsework segmentation, we have to create coarse mask for. So what we did was we took a kernel of size k by k, and we took majority voting inside it. And you can see that the red box now it's from refined. We have some coarse results where we have just one label for each small box. It's better than patch segmentation because it has more information, it's richer, but it has less information than the pixel wise. So it's like a spectrum. If we reduce the size of this kernel, we can reach to pixel wise segmentation, and if we just increase it to the patch, we'll go back to patch wise segmentation. So the network we design is we use DenseNet with small modifications. We replace the fully connected layer with fully convolution layer for our segmentation. There's no resizing in it, and no decoder is being used. It's just a simple encoder in it, which is base network. And then we use some additional residual network, residual layers actually, to improve the result further, because we are losing some information, so we wanted to enforce it more. So for training, we use the weighted loss function because there's been a class imbalance between them. So we used that, and we trained it for 100 epochs using RMS prop and adaptive learning rate of from 0.001 to 0.00001. So in our experiment results, to compare our approach, coarse segmentation with pixel-wise methods and patch-wise methods, because so we use two problems. One is OED grading, and the second one is survival analysis. So these are the downstream tasks, but we have intermediate tasks for which we need segmentation. The first one is layer segmentation, and the second one is tumor microenvironment segmentation. And we also calculated the inference time between the patch-wise and the core segmentation and the pixel-wise segmentation, that how they differentiate between in terms of accuracy. So for dysplastic grading, we used OED, and the first task was to segment the epithelium region into 3 layers: keratin, epithelium, and basal. And then once we have those segmentation results, we can grade the patch using the layer-wise nuclear features we'll see later on. So we used DeepLab V3 as a comparative pixel-wise segmentation network, and we divided we chose the kernel size of 116 and 32. For pixel-wise segmentation, we used we got the F1 score of 78.28, and as you can see that for mini patch 16, we got good results. It's better than the DeepLab because there has been a noise which was added. As you can see, we are going to more coarser, and it's not pixel perfect and DeepLab, and all those networks, they are computationally expressive and they are more specific toward those noise. But as CS9 is like simple encoder and using, because they have argmax max pooling layers, so it's naturally inclined towards getting those results. And similarly with rest of the mini patch 32, you can see the same results. It performed better. We cannot compare in between these cases because the ground truth has been changed. So you can see the prediction from here. So you can see we lost some of the details which we can see in the ground truth, and but overall it preserved the structure. So we can use these because we were mostly interested in the layers. We wanted to separate the layers. So minor details can be ignored because we average the results later on. So for downstream analysis, we extracted nuclear features using HoverNet and for each layer, and we stratified the patch into low risk versus high risk using those nuclear features. As you can see that we got comparative results if in here and same results for when we had the mini patch equal to 32. So it proved kind of thing that this core segmentation is comparative in compared to pixel-wise segmentation when we are using patch size, the kernel size of 32, and we get almost the same performance in downstream analysis. So in terms of time, we can see that the patch-wise segmentation is computationally expensive. It's almost around 20 hours. For pixel-wise segmentation, we have almost 30 minutes, and for our proposed network, it's like 20 minutes. It's been faster and achieves the same performance. It's less computationally expensive as well. So the second test we did, we performed on head and neck squamous cell carcinoma, and we divided it into tumor lymphocytes and tumor-associated stroma regions. And then once we have that tumor microenvironment segmented, we calculated the TASL score for survival prediction. So to compare the performance of a simple patch-wise segmentation with our network, we restricted the label assignment to just 32 by 32 because we are using the kernel size of 32 by 32 for a patch. So we take a patch of 256 by 256, but we assign the output to just 32 by 32 so that we can have the same kind of result. And we choose the stride of 32 because we can go to next 32 by 32 kernel size. And we can see that our network performs better because it has more context. It knows more about the other because it's richer than this one label. So as you can see in the prediction, we have because if you predict one wrong patch, you can get these kind of artifacts again because we average it, so we can get rid of these. So there are some false positives, but in a downstream analysis, they can be ignored. So once we have the tumor microenvironment, we calculated some factors, co-occurrence factors, which included the co-occurrence of stroma with lymphocytes, stroma with a stroma, and with tumor itself. So then we came up with this TASL score. It's been published separately as a paper, and we using this score, we stratified the patients. We plotted the Kaplan-Meier curves, and then we used log rank to stratify between high risk and low risk. I can see that it can do better job, and we got p-value which is significant 0.002. So the take-home message is that it's a middle ground. It's less computationally expensive. It doesn't require pixel-wise annotations, and it is comparable to other approaches, even better than patch-wise, and it's more suitable when you do not need pixel-wise annotations for your downstream analysis. Thank you. Any questions?
Thank you for the presentations. Are there any questions from the audience? Or if you for the participants from the remote participants, if you have questions, please raise your hands or type the question in the chat. So maybe let me ask the first question. It's quite interesting that you use kind of like Cosmo annotations to train the networks, which might potentially save the efforts in preparing the data. And can you tell us a little bit more about how you obtain the cost annotations?
Yeah, so basically we present a patch to pathologist with a grid of 32 by 32. We can choose the grid, and then he can just simply do the clicks, select the tumor, few clicks, the tumor has been marked. So we just present him with a tool where is the patch, and it's been graded, and they can just click on the grids, and we can get an annotation.
Okay, thanks.
Thank you.
So are there any other questions?
So 3 questions.
Yeah,
So
sure.
for clinicians, they used to looking at the full resolution images. You present like a hospital are they be able to do that properly, or there will be like variations for different clinicians?
So we didn't experiment with multiple conditions. We have one pathologist, and we gave him a simple patch, which we extracted, and then for incorporating enough context so that he knows that what it is. We didn't give him the full WSI. For the other case, he was using the full WSI. It's oral epithelial dysplasia. So basically, dysplasia is a pre-malignant state. It can convert into carcinoma. So we want to predict beforehand that if it is a dysplasia, so we can just look into it. If it is severe grade dysplasia, we can just tell the pathologist to or surgeon to remove it or treat it properly before it converts into cancer.
So are there any other questions?
First of all,
Please.
for your presentation. So,
Okay.
I'm wondering about the annotations. There you say that you have the whole slide being annotated by a single expert.
Yeah.
So this is not a bias in the annotation because you need at least compare with a set of experts.
Yeah, but
Have you considered that how you bias into annotation?
no, because we don't have any other annotations. So yeah, it's a good question. Yeah, we should look into it.
Thank you.
Thanks. Yes, please.
I have a quick comment here. So
Yeah, sure.
basically, you are using HE and slice, right?
Yeah.
So there in the public domain, there are lots of big data sets in pathology with HE slice, and so there are lots of robust or accurate models that you can use. Why you want to do this again?
So basically for dysplasia, we don't have enough, like I don't know any of public data set, but yes, for head and neck, we have it in TCGA. So basically the aim is that we don't have enough pixel-wise segmentations for head and neck. We might have for breast and lung, but for this, we don't have enough, which mark the tumor, stroma, lymphocyte, and these regions. So that's why we wanted to work on it and to do it on a mass scale and more in a faster way. We came up with this course annotations. So that answers the questions. All right, thank you.
Yes. So are there any other questions? I guess the audience happy with that. So let's move on to our next speaker. Thank you, Stas, for yes. So our last speakers in this session is Mikhail Brufers from King's College London. Mikhail is presenting remotely as well. So Mikhail the title of his talk is Fitting Segmentation Networks on Varying Image Resolutions Using Splatting. Welcome, Mikhail. Now the stage is yours.
Thank you very much. Thank you. So I can't be here in person. I'm Mikhail, and as was already told, I'll be presenting our work on fitting segmentation networks on different image resolutions. So this connects a little bit to the question that was asked at the end of the first talk, I think. Anyway, let's go. So let's say we have medical images of different subjects. For example, what is shown in this slide, T1 weighted brain MRIs. In the raw format, these images are commonly defined on different grids, that is with different dimensions, orientation, position, etc. In order to fit a segmentation network like a unit with a batch size greater than 1, a resampling operation is usually performed. This operation ensures that all images have the same grid, so they can be stacked in the batch dimension. The same is often true for multi-channel data of the same subject, like the T1, T2, and proton density weighted scans shown here. Again, resampling can be performed to stack the multi-channel images. However, there are some issues with resampling. It can introduce partial volume effects as well as values that are not present in the original images through interpolation. It has a smoothing effect, which effectively reduces the observed noise variance of the image. It does not inform the segmentation network on how confident it should be about the particular voxel value, that is, whether it has been highly interpolated or preserves the raw value. Therefore, to overcome these issues, we in this work propose the use of something known as a splatting operator as a layer in a segmentation network. The splatting operator is the adjoint of the resampling operator. The splat layer does not interpolate voxels, but rather pushes them onto a so-called common image mean space. It is in this mean space that the network will do the forward pass. Integrating this splat layer at the head of the network means that no prior resolution adjustment like resampling is needed as a pre-processing step. So to try to get you guys an idea of what this splatting operator is, I'm going to give a simple example. I hope it will clarify this, comparing it to resampling, and this is all in 1D. A generalization to n dimension is in the paper. You can look at the message section if you're interested. So first, let's introduce some notation. We have M subject images with C channels. T here is the mean image. F is the data, like an MR image. N is the number of observations or voxels in the case of an image. C is a count image. A is an affine map that maps from voxel to millimeter world space, often encoded in, for example, the nifty header. I is identity grid, and phi is a deformation. Okay, so let's say we have an input image with 4 voxels. We have an affine matrix that only encodes a scaling, and this identity grid uses the spatial location of each value in the image. The mean space is larger and will contain 8 voxels. Its affine matrix is simply an identity here for simplicity, and you can see the identity grid is larger, as I said. So let's first use resampling to create the mean space. So resampling basically involves pulling voxels from the image using a deformation, defining the mean space in some form of interpolation. So we define the deformation is based on a composition of the 2 affine matrices from the mean space, denoted T, to the image space, and this is the inverse. This basically decides which voxels to pull from the image to the mean space. So that gives us deformation by multiplying this affine transformation with the identity grid in the mean space, and this basically gives us the resampled values in the mean space. Okay, splatting on the other hand, it's different because it doesn't interpolate. This is the key key thing to note about this operation. So in this case, we compose the affine matrices the other way around, and then the identity grid is now defined in the space of the image. So we basically affinely transform this identity grid, and then we push voxels to the resample, or not the resample, to the new space, mean space. Okay, so we get actually different values whether we resample or we splat. And importantly as well for the splatting is that we have a count image which tells us how many voxels were pushed to each location, which is this sort of confidence of how much each voxel is weighted in the sort of mean space. Okay, so this is sort of like the idea. So then what is very important to also note is this thing I said earlier about adjointness. So you can actually encode resampling just as a large sparse matrix multiplication. It's the equivalent. And you can also actually do this with splatting. So this is just like a side note. There's more information in the paper because I know this might be a bit much to take in. The important thing is that the two operations are actually adjoint operators. And this is important when we put this into a segmentation network, because we will have one operation at the head and one operation at the tail of the network. So I'll say a bit more about this in the next slide. Okay, so now let's talk a little bit about how this is integrated. So first of all, we make a CUDA implementation publicly available for these operators. And then, as I said, we put the splat layer at the head of the network. So this basically means that we can have input images of any dimensions, and as part of the network forward pass, the voxels are pushed into the mean space. So there's no prior resampling needed. And then, as I said, there's like this relationship between the two operators, right? Between push splatting and resampling. So what we do is that we push into the mean space, and all images of different channel subjects are in this mean space. The forward pass is performed, and then you get your predicted segmentations. And then the adjoint operator basically pulls the predictions back into the native image space where the loss is computed. So we get the loss computed in the space of the native labels and images, but the whole forward pass is done in this sort of common space. Okay, so important to note. So that basically means that the first and last layers of the network are adjoint operations, which is similar to a UNet where you have the encoder and the decoder being adjoint operators. So it integrates nicely into that type of architecture, basically. Let's also move on. So like I said before, there's more about the generalization in the paper. So what is this mean space I've been going on about? Well, it can be computed in different ways. It's basically just like some dimensions, some voxel size, some orientation defined by an affine matrix. So we define the mean space is based on all the affine matrices of all training images. So it's sort of like covers the field of view of all the training images. And then we constrain the dimensions to be a power of 2 or 3, because this just facilitates fitting these sort of like coarse-defined encoding decoding architectures. And for all the experiments in this work, we used 192 cubed dimension and 1 millimeter isotropic voxels. Okay, so there is like a slight computational overhead in splatting. It's not that big, but there's some of it. So let me just talk you through that. So the actual operation is linear in the number of native image voxels. So that's like resampling. There's no difference. But if the operation is parallelized, since you can push voxels into the same locations, you need atomic assignments to avoid collision, sort of. And also the thing is that the count image basically doubles the number of input channels into the forward pass, because we need the information from this count image. Okay, but the splatting operation can be done offline beforehand, which saves time, and then but only needs to be done online is this sort of resampling at the tail of the network that I was talking about. Okay, so that's sort of the methods section, and I'm happy to answer any questions at the end if there needs more clarifications. So how did we validate this then? Well, we wanted to investigate if using this splatting operators inside of a network would improve MRI brain segmentation when we had multiple contrast images per subject, like for example here, a flare T1 and a T2, and the images had different resolutions, and the labels were defined on one of the images. Okay, so to do this, we defined a baseline network. This was a simple UNet with a dice loss and sort of quite standard. And then we had two sort of methods of using this baseline network. One was, which we call UNet, was just to resample all the images beforehand as a pre-processing step to have the same dimensions, 192 cube. Another one, which we call mean space net, is to integrate these splat layers, so there's no resampling needed, basically. And then we performed these experiments on simulated and real data, and it's all publicly available data, by the way. So the first experiment used 97 subjects from this TCGA GBM dataset. The example scans and labels are shown here. I had 4 MR contrasts, as you can see. The thing about this data set is that this had already been resampled to 1 millimeter voxel size and had the same dimension. That's why we sort of artificially needs to create varying resolution scans. And each subject had 3 manually delineated labels of different tumors and edema and so on. So the experiment went like this. So we simulate fixed light data by just downsampling in random direction, all of the scans. And then, as I said, we either fit the UNet to already pre-processed versions to 192 cube, or we fit this mean space net to directly downsample data. And we have this train val test split 40-17-40. And our metric for our validation is just a pairwise size between predicted and ground truth labels. So the results were encouraging, as you can see in the table and the box plot here. So the mean space net significantly with the Wilcoxon test outperformed the UNet for all these different labels. As you can see, this is the median is 0.677 for all classes compared to 0.528 for the UNet. So that's encouraging. And now next we want to investigate if this translates to real data, where we don't do any sort of downsampling beforehand. So this time we use 7 subjects, which is not that many, for sure, but anyway, that's what we did from this MR Brain S18 challenge. And there's 3 MR contrasts. Again, you see the images here, and you see the labels. There are a bunch of different labels. I'll tell you more about these soon. The T1 weighted had 1 millimeter voxels, and because these images were raw in the sense that they were only basically converted from DICOM to NIFTY. That's it. There's nothing else done. No skull stripping, resampling, bias correction, whatever. So and then the T1, the T2 flare had 0.96, 0.963 millimeter voxels. So they vary, and the dimensions too. And then we used 7 labels, which were annotated on the T2 flare. There were like 9 or 10 in total. We selected 7 of these labels to do our validation. So experiment this time, similar as before, we fit the UNet to 192 resampled versions of these raw input images, and also then the mean space net directly to the raw images without any resampling. And as we only have 7 subjects, we did like a leave one out cross validation and picked a random fold for the results we report. So yeah, that's how we did it, and the same metric. So the result this time, well, we saw significant improvements in 4 out of 7 classes. The median overall is 0.864 compared to 0.813 for the UNet. So it does look encouraging also here. We would require possibly a larger data set to do a more thorough validation, but the results, they do look pretty all right, I'd say. So you can see there's like a lot of different brain structures here that were in this label set. So key takeaways from this talk then. So we have proposed a splat layer that sort of removes the need for explicit resolution adjustment as a pre-processing step. it does not modify the input data. There's no interpolation done. There's only this pushing operation and a count image. So there will be no interpolation. We make a CUDA implementation publicly available, and we showed on 2 multimodal MRI datasets that this splatting operation does outperform resampling in our particular validation setting. There is a slight overhead in compute, as I said, mostly because we will have to increase the number of input channels. This type of approach could maybe streamline model development because you don't have to write separate code for pre-processing or resampling and so on. And as a future direction, it could be quite interesting. You could include, if you wanted to, because there is like a parallel to super resolution here with these adjoint operators. So you could include learnable parameters in your splat layers, and it could be the network could then be doing something like super resolution when you're fitting it. I haven't explored this yet, but these are just sort of ideas. So yeah, that's it. This is the GitHub with the implementation. Once again, I'm sorry I couldn't be there in person, and thank you so much for listening.
Thank you, Mikael. This is interesting. Any questions from the audience?
Thank you very much. This is very interesting. Tell me more about the counting. So it's probably an integer rather than a float. So it doesn't actually double if you decide to count. Is that correct? The counting.
It doesn't have to be an integer, actually. It depends. Like it's more of a, you can think of it as a weight, sort of like that tells you just how many voxels were pushed to each location. So in some places it could be 0, and there could be then sort of like holes in the pushed image, splatted image, because, and that's where this super resolution could be quite useful, because it could then help with dealing with these 0 regions. But yeah, that's sort of.
And you said the computational complexity increases slightly. So I assume that's it, because you use 2 data sets and both of them are relatively small, so you could probably fit them in the GPU. If you have a large data set, which every epoch you have to do the splatting again and again, is that going to change the computational complexity?
Oh, so yeah. Well, for here, I think we used like a batch size of 2 or 4 or something, because they're like, and still volumetric images still quite large.
Yeah.
But the head of the network where the splatting is performed could be done offline, that is beforehand, if you wanted to, so you wouldn't have to do that computation all over and over again. But when you go back at the end of the network, at the tail to the native images to compute the loss, you'll always have to do this sort of adjoint operator. So the compute isn't really like the actual like process of doing the splatting and so on. It's not what would probably take time. It's rather the fact that we would have to integrate this count image. So that would require a little bit more memory, and also you would take a bit more compute because you have more input channels in the network, sort of. I haven't thought that much about it. There might be clever ways of also trying to deal with this, but that I'd say is one of the main sort of overheads compared to not using this operator in the network directly, sort of.
Okay, thank you.
Welcome.
Thank you. Very interesting talk. So I'm sorry, this may be my lack of understanding, but I'm failing to understand why would this improve performance. So I can understand that, yes, there is a splitting operation going on, but where is the extra information coming on? So for UNet, you had data that was resampled, right?
Yeah.
So I would expect that to perform better, given that a network now has to learn all the differences between different resolutions. So where is the extra information coming from, or how is it dealing with that?
Yeah, well, the sort of idea that we were thinking was that, so you have your resampler preprocessed image, and you have quite 6 slice data, which means that the resampling step sort of integrates partial volume effects when it goes from a larger voxel size to a smaller voxel size, whilst not doing resampling beforehand and just integrating the raw data into the network doesn't what do you say, create data that isn't there. So you're basically providing the network with the raw observed data without any changes being made by an interpolation step. And then so the additional information is sort of implicit in that the network sees the raw data, and it also has information about how much weight there is to each of these voxels by the sort of count image. So it's sort of an implicit thing where the network would be informed about the raw image data and the count. So it's all the sort of, I guess, my sort of belief is that it's you wouldn't want to, if you have some observed data, you would want to make as little modifications to it as possible. Although deep segmentation networks would often require some sort of intensity normalization and so on to standardize, but that's sort of the idea.
Are there any other questions? Yes, I have a questions. So yes, I want, maybe I overlooked some of the details, but I wonder if the mean space in your networks is the dimensions of the mean space always larger than the dimension of the input space, and how does this result? I mean, in terms of the computation effort.
Yeah, that's a great question. So basically, you can define the size of the mean space yourself. So you could have a larger voxel size if you wanted to, and then you would have much faster computations. But then you also would lose out a bit of resolution if you had 2 mm voxels, for example. Or you could have a smaller field of view, but then you could actually, parts of the image might not be included in this sort of mean space. So we set it to 192, sort of bit based on an average dimensions of all the training images, but you want to make it sort of as small as you possibly could, because otherwise you will just introduce unnecessary compute. And then what we simply set vox, like if the image is smaller, then we just, when if it pushed into this mean space, we set them to 0 outside, and if it's larger, then you could miss out on a bit of the field of view. So it's an important thing to think about when you do this. So yeah, that's a good question.
Yes, I think we are on time for the coffee break now. Yeah, let's finalize these sessions by thank you to all our 3 speakers again.